you explain why you came up with that?
Well, the area of the space is W times W, which is just W squared.
Okay.
And then you have four sides that's area is equal to W times L. That prevents you from accidentally adding the top as well.
All right, so if we had a top on this, then we would have had two W squareds in here, but in this case we don't, so we have just one W squared. All right, are there any questions on that formula? Any thoughts or ideas? Okay, so this seems pretty reasonable. If we want to come up with the area of this box, the surface area of the box, we need the area of the base. And the base is a square, so its area is W times W. And then we need the area of each side. And all four sides have a length times a width to come up with one of those areas. And so we've got four of those. Okay, great. So this is our formula for surface area. So this is step number one. We need to come up with an equation which describes the surface area of the box. Now when I look at this formula, in this case, we unfortunately have two variables over on the right side. So we're going to need to come up with a relation between L and W where we can solve for one of the variables and plug it into this formula so that we end up with just one variable in our area formula. Okay, so I go back over here to my statement. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. So the only other piece of information I have in here is the 32,000. And so I know that my volume, so a second relation, is that I know that volume must be 32,000. And if I want to know the volume of a box, what do I need to know? Yeah, the volume of a box is length times width times height, which in this case is W times L. So 32,000 is W squared times L. Okay, so this is our second relation. It's a relation that relates W and L, and W and L, their connection is equal to some number. And we can take this equation and solve for one of the variables. Now, in this case, I would recommend that we solve for L since W is squared in here. So if I solve for L, we have L is equal to 32,000 over W squared. And so now when I go back to my area formula, I've got that area is equal to W squared plus 4 times 32,000 over W squared times W. And so at this point, we have a formula for area, where area is some function that depends only on one variable, only on W. Are there any questions about coming up with this formula? This is half the battle on these problems. Okay, half the battle is coming up with this formula. The next thing that we want to do is to, eventually we'd like to figure out where is the area the smallest. So what we're going to do is we're going to take our derivative, set that derivative equal to 0. That'll give us a flat spot, hopefully the bottom of a bowl, and then we can go from there. Now if I want to take this derivative, it's in my best interest to simplify this a little bit first. So some things I can do, I've got area is equal to W squared plus, what's 4 times 32?
128.
Yeah, so we have 128,000, and then we have W to the negative 1, okay, because we have W over W squared. Okay, so this is our area formula. Area is equal to W squared plus 128,000 W to the negative 1. Okay, here's where the calculus comes in. We want to figure out where area is the smallest, so we're looking for the bottom of a bowl. So we want to take our derivative, 2W, minus 128,000 W to the negative 2, and then we want to set that derivative equal to 0. So we've got 0 is equal to 2W minus 128,000 W to the negative 1. negative 2. Thank you. I lost one of those W's. W to the negative 2. Okay. Any questions so far? Okay. So now we want to solve this equation for W. One of the issues that I'm running into here is this W to the negative 2. And in order to solve this, so in order to take the derivative, it makes sense to write W to the negative 1 so I can use the power rule pretty quickly. But in terms of solving an equation, it's easier to not have variables raised to negative power. So in terms of the algebra, it might make sense for us to write this as 0 is equal to 2W minus 128,000 over W squared. And so now if I want to work with this, I still have W's in the denominator, and I really don't like having W's in the denominator, so I can do one of two things. I can either find a common denominator and then eventually clear out that denominator, or to get rid of this denominator, I can multiply everything by W squared. So whatever I do, I just want to get rid of that denominator. So if I multiply the left and the right side by W squared, on the left side that does nothing. I still have 0. And on the right side I have 2W to the third minus 128,000. Alright, so that was my algebra technique. I got rid of my denominator. And in the process of doing that, life got pretty nice. I ended up with 2W cubed minus 128,000. If I still want to solve for W, what's my next step? Yeah, let's remove that 128,000, so we'll add that to both sides, and we have 128,000 is equal to 2W cubed. We can divide both sides by 2, and we have W cubed is equal to 64,000. So now the next question becomes, and I see everyone going for their calculator, finding the cubed root of 64,000. 40? So getting a value of W equals 40. Do I have a second on that number? Yes. Okay, great. So W is equal to 40. Okay, so a few things that we need to do with this. We have found our formula for surface area. We've taken the derivative, set that derivative equal to 0, and solved for W. So this value of W gives us a flat spot on the graph. Jennifer?
Never mind, you answered it.
Okay. So this value of W is a place where the area function is flat, where the derivative is equal to 0. So one thing we need to do is to make sure that this value of W, check that W equals 40 yields a minimum rather than a maximum. Because it would be a really bad idea if we went back to our supervisor and told them that we want a box whose base is 40 by 40 that minimizes the material used, but in fact it actually was the top of a hill and maximized the amount of material used. Your boss would not be very happy with you. Okay? So that's one thing we need to do, and then we need to go back and answer the question about the dimensions. So let's make sure that we have in fact found a minimum rather than a maximum on our area function. There's a couple of ways to do this. One is to look at our first derivative and plug in W values before and after 40 to show that our original function A went downhill and then uphill. So in other words, if we plug in a value less than 40, then A prime should be negative, and then the value after 40, A prime should be positive. The other option is to look at A double prime, and that's what I'm going to do here. So since A prime was 2W minus 128,000 W to the negative 2, Well, if I look at A double prime, then I have 2 plus, okay, so this is 256,000 W to the negative 3. And so if I'm looking at this expression here, my A double prime is 2 plus 256,000 over W cubed. And as long as A double prime, so our second derivative talks about concavity of the original function, right? And so as long as our A double prime is positive for all of our possible W values, then we have a graph that is concave up. Now, in terms of our example, we're talking about W being the length along the side down here, so that number's got to be greater than or equal to 0. Now, 0 wouldn't really make any sense. So W is always a positive number, which makes A double prime always positive. A double prime is positive, so A is concave up. So the shape of our graph is an upward-facing bowl, which means that our value of W is going to be a minimum. So we have a minimum at W is equal to 40. So here we're using the calculus to justify that we have a minimum rather than a maximum. And our final step is to actually answer the question. Find the dimensions of the box that minimize, find the dimensions of the box that minimize the amount of material used. So when we want to find the dimensions, that means that we need to say what W is and what L is. So our dimensions that minimize the amount of material used those dimensions are W is equal to 40 centimeters and L, well, how can we figure out L? Yeah, we can use our formula that we came up with for L right here. So L will be 32,000 over W squared, so over 40 squared. And I will need help with that. 20? Do I have a second on 20 centimeters?
Yep.
Yes. Great. Okay. So the dimensions for our box are 40 centimeters by 20 centimeters. 40 for each side of the base and 20 for the height. Well,
so I was wondering if you'd be able to do like an example where you don't have a polynomial whatever equation, because just look at the W squared, so you know.
well, this is not a W squared, this is W to the negative.
The first one is. That's 128, yeah.
This is, but once we account for the L, it becomes not polynomial anymore. It becomes a rational function, because this is really, I mean, if I rewrite this as W squared plus 128,000 over W,
Yeah.
I would write, to come up with a common denominator, I'd have W cubed plus 128,000 over W. This is really the function that I'm minimizing. So it's really not a polynomial function, it's a rational function. You don't like that so much.
I don't know, maybe I'm just.
So, I mean, so your comment the other day was that, you know, if we have a quadratic function, it's a parabola, and we already know everything about parabola, who cares? But this one is different from a parabola. This one is, in fact, a rational function. And so the knowledge that we have about parabolas is not going to give us any information about this.
I had a question about A double prime.
Yes.
Where you have W cubed, you're saying it's positive. Now, if it were only squared, would it then be able to be any number?
No, so the cube is really not what makes the whole thing positive. It's because our W is measuring a length.
Okay.
And so W is definitely going to be positive.
Okay.
So W cubed is definitely going to be positive.
Okay.
And so this whole piece is positive, and then we're adding that on to another positive number, so the whole thing had better be positive.
Okay.
Okay, so all of this is all the calculus that goes along with this, but I like to see pictures too. So if I was working on a problem like this, what I might want to do to convince myself that life is okay is I might graph this area function on my calculator. So let's take a look at what that looks like. So we have x squared plus 128,000 x raised to the negative 1. And we graph, and based on whatever the heck I had in here before, there's some kind of a crazy looking picture. Okay. So first thing I'm going to do is I'm going to change my window. And I've played around with this before, so a good window for this, well, first of all, we know that the x value, that's our W, has to include 40. So maybe I'll go 0 to 100. And I know that the height of my function is describing surface area, and surface area is never going to be negative. So my y minimum will be 0. And I would need to play around with the y maximum. But I have already done that a little bit, so I'm going to type in 15,000 and go with that, and hit graph. And so what we get is a picture of part of a rational function, where if I type in x is equal to 40, if I do trace and type 40, then when x, or in our case w, is equal to 40, the height of our graph is 4,800. Now that height is representing the surface area. So we plug in x equals 40, and the surface area will be 4,800 square centimeters. Okay, and that is the smallest amount of surface area that we can have for a box with a volume of 32,000.
Now, if we graph it, because I tried graphing it as 128,000 over W, without Tony, I get something completely different.
You get something completely different.
I have like a horizontal asymptote, and then it doesn't even, 40 is not even on there. I do calculate value for 40, and it's not even there.
X squared plus 128,000 over x. That's really strange. X goes from negative 10. Well, so one issue is that your window is going from negative 10 to 10. So you're getting the part where you will have a vertical asymptote there at x equals 0. So my vertical asymptote is over here on the left. So change your x window from 0 to 100 and see if it helps your picture. It helps? Okay. So that's a window issue. Okay, so this is our picture. The x-axis is describing W, which is the length of the base, and the y-axis is describing the area. Okay, any questions about this one? Other questions? Okay. All right, so that brings our discussion about optimization problems to a close.